These are the answers to the practice quiz on polarity, intermolecular forces, and properties of liquids and solids. In the video description area, there is a link to the packet that accompanies this video. Question 1 of the practice quiz says the following. Electronegativity values are used to compare atoms of different elements on the periodic table with respect to how strongly the atom attracts or pulls in the shared electrons in a covalent bond. And so in part A, it says, as you move left to right across a period, electronegativity values tend to. So here are the electronegativity values for various elements on the periodic table. And as we move from left to right across a period, for example, lithium 1.0, beryllium 1.5, boron 2.0, carbon 2.5, nitrogen 3.0, oxygen 3.5, and fluorine 4.0, we can see this horizontal trend that as you move from left to right across a period, electronegativity values tend to increase. Now, with respect to the vertical trend, as you move from top to bottom down a group, electronegativity values tend to, and we'll take a look at group 1. So we have hydrogen 2.1, lithium 1.0, sodium 0.9, potassium 0.8. So we can see that as you move from top to bottom down a group, electronegativity values tend to decrease. Now let's take a look at question 2. It says each atom in a polar covalent bond can be labeled with a partial positive charge, so a delta plus, or labeled with a partial negative charge, delta minus. And the instructions in question 2 say circle all of the polar covalent bonds in the table below that have been labeled with the appropriate partial charges. So as we answer question 2, we're going to use the following rule to guide our answer choices. In a polar covalent bond, the atom with the higher electronegativity value has a stronger attraction for the shared pair of electrons. The partial negative charge is located on the atom with the higher electronegativity value. So to answer question 2 correctly, we need to rely on our knowledge of both the horizontal and the vertical trends in electronegativity. All right, let's start with the carbon-oxygen bond. The first thing we're going to do is locate these elements on the periodic table. So there's carbon, there's oxygen, and we can see that they are located in the same period. And as you move from left to right across a period, electronegativity values tend to increase. So this means that oxygen, which is further to the right, is more electronegative than carbon. Now, since oxygen is more electronegative than carbon, the oxygen atom should have a partial negative charge. So this particular bond has been labeled correctly with the appropriate partial charges. Our next bond to consider is the bond between chlorine and iodine. Let's go find chlorine and iodine in the periodic table, and we can see there's chlorine and there's iodine. So they are located in the same group. And as you move from top to bottom down a group, electronegativity values tend to decrease. So this means that chlorine is more electronegative than iodine. And if chlorine is more electronegative than iodine, then that means that the chlorine atom should have a partial negative charge. But since in this particular bond, chlorine has been labeled with a delta plus, this bond has not been labeled with the appropriate partial charges. All right, our next bond to consider is the bond between fluorine and boron. So on the periodic table, there's boron, there's fluorine. As you move from left to right across a period, electronegativity values tend to increase. So since fluorine is further to the right, that means that fluorine is more electronegative than boron. Now, since fluorine is more electronegative than boron, then the fluorine atom should have a partial negative charge. So this bond has not been labeled correctly with the appropriate partial charges. All right, moving on to our next bond. This is the bond between hydrogen and fluorine. So we can see that hydrogen is on the left, fluorine is on the right. That's a pretty significant difference. And In general, as you move from left to right across a period, electronegativity values tend to increase. Even though hydrogen and fluorine are not located in the same period, this is still consistent with that horizontal trend. We would expect fluorine to be more electronegative than hydrogen, especially considering how far apart they are on the periodic table. Now, since fluorine is more electronegative than hydrogen, then the fluorine atom should have a partial negative charge. So this bond has been labeled correctly with the appropriate partial charges. Our next bond to consider is the bond between silicon and sulfur. So there is silicon and sulfur. They're located in the same period. Again, electronegativity values tend to increase from left to right across a period. Sulfur is further to the right compared to silicon. We would expect sulfur to be more electronegative than silicon. And since sulfur is more electronegative than silicon, then the sulfur atom should have a partial negative charge. So this bond has not been labeled correctly with the appropriate partial charges. And then the last one to consider in question 2 is the bond between nitrogen and arsenic. So nitrogen and arsenic are located in the same group, and as you move from top to bottom down a group, electronegativity values tend to decrease, so therefore nitrogen should be more electronegative than arsenic. And since nitrogen is more electronegative than arsenic, then that would mean that the nitrogen atom should have the partial negative charge. So this bond has been labeled correctly with the appropriate partial charges. All right, well, hopefully all of those answers and explanations make sense to you. Now, let's take a look at question 3 in this practice quiz. In question 3, it says, answer the following questions related to Lewis electron dot diagrams, molecular shapes, polarity, and intermolecular attractive forces. In part A, it says, complete the Lewis electron dot diagrams for CO2 and H2S by drawing all of the bonding pairs of electrons and non-bonding pairs of electrons. Now, before I complete the Lewis electron dot diagram for CO2, I think it would be a good idea to review the general strategy and procedure for creating Lewis diagrams. So Lewis diagrams show how atoms are connected to each other in molecules and polyatomic ions. In a Lewis diagram, electrons are arranged in pairs, so groups of 2 electrons. A bonding pair of electrons is also known as a shared pair of electrons between atoms, and this is normally represented as a dash between 2 atoms. An unshared pair of electrons, also known as a lone pair or a non-bonding pair of electrons, this is normally represented as a pair of dots close together. The octet rule states that an atom, usually a nonmetal in groups 14 to 17, tends to form covalent bonds in such a way that is surrounded by a total of 8 valence electrons. Hydrogen does not obey the octet rule. A hydrogen atom only forms one single bond, giving it access to a total of 2 valence electrons. Here are some examples of what Lewis electron dot diagrams will look like for molecules and polyatomic ions. So the procedure for creating a Lewis diagram starts with the following. Step 1, count the total number of valence electrons in the molecule or polyatomic ion. This number represents the total number of electrons that you should use to create the Lewis diagram. Step 2, connect the atoms together to form a skeletal structure. Start by connecting atoms with single bonds represented as a dash. Each single bond is a bonding pair that represents 2 electrons. Step 3, if any atom on the edge of the Lewis diagram does not have access to a complete octet, add lone pairs of electrons around the atom to complete the octet for that atom. A lone pair is represented as 2 dots close together. Remember that hydrogen atom will only form a single bond and does not obey the octet rule. And then finally, examine the central atom or atoms. If each atom in the Lewis diagram, except for hydrogen, has access to an octet of electrons, the Lewis diagram is complete. If a central atom has less than an octet, then you will need to move one or more of the lone pairs from the atoms on the edges to create double bonds or triple bonds. Continue this process until each atom in the Lewis diagram, except for hydrogen, has access to a complete octet. Now let's go back to question 3, part A, and let's complete the Lewis diagram for carbon dioxide. First, I'm going to count the total number of valence electrons in this molecule. So carbon has 4 valence electrons. Oxygen has 6 valence electrons. Therefore, the total for CO2 would be 4 plus 6 plus 6, so that's 16 valence electrons. I'm going to start by connecting the atoms with single bonds. Now I'm going to complete the octet for each oxygen atom. So this oxygen atom on the left has access to a complete octet, so 2, 4, 6, 8. I'll do that same process on the other side of the molecule. So now this atom has access to a complete octet. But if you count the total number of electrons that I have used so far, including the bonding pairs, the dashes, and the non-bonding pairs, the dots, you have already used 16 electrons if you have created the Lewis diagram so far. So we can't continue to add more dots on the carbon atom. And hopefully you can see that this carbon atom only has access to 4 electrons with those 2 dashes. So the carbon atom does not have access to a complete octet. So what I'm going to do is create a double bond on the left, and I will also create a double bond on the right by moving a pair of electrons to create that double bond. So now let's consider the molecular shape of CO2. The molecular shape of CO2 with those 2 double bonds, one on the left and one on the right, is going to be linear. So you can see other shapes are listed here on this slide. We have bent, trigonal planar, trigonal pyramidal, tetrahedral, but the CO2 molecule is linear. So in part B of this question, it says, based on the Lewis diagrams that you drew in part A, the CO2 molecule is, and the answer is linear. Now, what about classifying CO2 as nonpolar or polar? What I've done now is I've drawn these 2 arrows going from the carbon to the oxygen, but in opposite directions. Those 2 arrows represent the polar bond. So there's a polar bond between C and O, but there's one on the left and there's one on the right. So these 2 polar bonds, which are also known as dipoles, are oriented in opposite directions. So based on that symmetry, these dipoles cancel each other out. And so CO2 is classified as a non-polar molecule. Now what I'm going to do as we go through different examples of molecules in this practice quiz is I'm going to classify non-polar molecules on the left. They're going to be fairly symmetrical, in which all of the bond dipoles cancel each other out. And then if we find any polar molecules, I will place them on the right. Polar molecules tend to have some asymmetry. They're asymmetrical and their bond dipoles do not cancel each other out. So CO2 is classified as non-polar. Now, CO2 is a linear molecule and it happens to be non-polar. You might be thinking, are all linear molecules classified as non-polar? Well, the answer to that question is, it depends. It depends on the symmetry of the molecule. Is it possible to be a linear molecule but to be polar instead of non-polar? Here's an example. So this is a hydrogen bonded to a carbon bonded to a nitrogen. There's a single bond on the left, there's a triple bond on the right, and so this molecule, HCN, does not have that same symmetry that carbon dioxide does. So these are different atoms. There's a hydrogen, a nitrogen, so these bond dipoles do not cancel each other out. So could a linear molecule be either polar or non-polar? And the answer is yes. It depends on the symmetry of the molecule. All right, so now we know that CO2 is linear and non-polar. Let's go ahead and take a look at the process for completing the Lewis diagram for H2S. So hydrogen has 1 valence electron. Sulfur has 6 valence electrons. So the total number of valence electrons in the H2S molecule would be 1 plus 1 plus 6. So we have 8 valence electrons. I'll start with the dashes. Remember that hydrogen does not obey the octet rule, so I don't need to surround the hydrogen with dots. Only one single bond is enough for hydrogen. So that means that the hydrogen is complete in terms of what it needs, but I need 8 valence electrons total, and so far I've only used 4 in the 2 dashes. So there's 6, 8. Now that molecule is complete. Now the CO2 was a linear molecule. The CO2 did not have any lone pairs of electrons on that central carbon atom. But the H2S does have 2 lone pairs of electrons on that central sulfur atom. So will the H2S be linear or bent? Let's take a look at the different shapes of the molecules, and we'll see if H2S is going to be linear or bent. Hopefully you can see that the presence of at least 1 lone pair of electrons on that central atom will cause that molecule to be not linear, but bent. So the presence of the lone pairs of electrons on that central sulfur atom will affect the shape of the molecule. So CO2 was linear, H2S is bent. And I'm going to go ahead and draw it like that just to emphasize what that molecule looks like. It does have that bent shape. Now, is it polar or nonpolar? Well, there are the polar bonds. So there's a hydrogen-sulfur bond, and there's another hydrogen-sulfur bond. But unlike the CO2, these are not oriented exactly opposite. They're not exactly going to cancel out. So these 2 polar bonds, or the dipoles, are pointing at an angle. They're not exactly 180 degrees apart like they were for CO2. So these dipoles do not cancel each other out. H2S is classified as a polar molecule. So again, I've got nonpolar molecules that are symmetrical, in which all of the bond dipoles cancel each other out. And now I can see some polar molecules that have an asymmetrical shape, or an asymmetrical arrangement of atoms, and the bond dipoles do not cancel each other out. You might be thinking, H2S is a bent molecule. Are all bent molecules classified as polar? And the answer is yes. A bent molecule will always be classified as polar. The dipoles do not cancel each other out. Okay, now we're ready to take a look at part C of this question. So in part B, we learned that CO2 is linear and nonpolar, and we learned that H2S is bent and polar. So in part C, it says, based on your answers to parts A and B, circle all of the intermolecular attractive forces that each substance can experience. Now, the 3 types of intermolecular attractive forces that a molecule can experience are London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. Again, these are attractive forces between molecules. So what's the rule for deciding whether or not a molecule will experience any one or all 3 of these attractive forces? Starting with London dispersion forces, it doesn't matter if the molecule is classified as polar or nonpolar. All molecules can experience London dispersion forces, or LDFs for short. Now, for dipole-dipole forces, you have to be polar. So only polar molecules can experience dipole-dipole attractive forces. And then for hydrogen bonding attractive forces, a molecule has to contain a hydrogen directly bonded to either a nitrogen or an oxygen or a fluorine in order to experience hydrogen bonding attractive forces. Now, for CO2, it is classified as nonpolar, so it can definitely experience London dispersion forces, but that's it. Not dipole-dipole forces, and obviously there's no hydrogen, so no hydrogen bonding for CO2 molecules. With respect to H2S, it is polar. It can experience both London dispersion forces and dipole-dipole attractive forces because it's polar, but the hydrogen is not bonded to nitrogen or oxygen or fluorine, so that's it. All right, let's go ahead and move to our next question in the practice quiz. It's going to be a similar type of problem to question 3. So here in question 4, we have 2 Lewis electron dot diagrams that we must complete for NH3 and SO3. So starting with NH3, hydrogen has 1 valence electron, nitrogen has 5 valence electrons, so in the NH3 molecule, that would be a total of 1 plus 1 plus 1 plus 5, that's 8 valence electrons for the NH3 molecule. So there are my dashes. I've just used 3 dashes. That would be 6 electrons. I only have 2 more electrons to use. Remember that hydrogen will not have any dots around it, so the last pair of electrons will go right there on the nitrogen, which does give that atom access to a complete octet. So what are my choices for shapes for the NH3 molecule? Well, it's not going to be linear or bent. It's either going to be trigonal planar or trigonal pyramidal. And the question comes down to, is there a pair of electrons on that central atom? And the answer is yes. You can see it right there. So that lone pair of electrons on that central nitrogen atom will cause NH3 to have the shape that we know as trigonal pyramidal. So what about trigonal planar? Well, that might be featured in another molecule later in the video, but NH3 is definitely classified as trigonal pyramidal, and that presence of that lone pair on the central atom affects the shape of that molecule. So NH3 is trigonal pyramidal. I'm going to go ahead and draw it like that to emphasize that trigonal pyramidal shape. Is it polar or nonpolar? Let's decide if the bonds, the dipoles, the polar bonds in the NH3 molecule, are they going to cancel each other out? Well, the answer is no, they do not cancel each other out. These 3 polar bonds or dipoles, they're all pointing at an angle. So it's similar to a bent molecule, that these dipoles do not cancel each other out. So NH3, with its trigonal pyramidal shape, is classified as a polar molecule. I'm going to place it on the right in this classification that I have so far. So I've got CO2, linear, symmetrical, nonpolar. I didn't actually show you HCN in the practice quiz, but I mentioned it earlier in the video as a linear molecule that does not have the same symmetry as CO2. So there's an H2S, which is bent, and there's an NH3, which is trigonal pyramidal. You might be thinking, if NH3 is a trigonal pyramidal molecule, are all trigonal pyramidal molecules classified as polar? And the answer is yes. A trigonal pyramidal molecule will always be classified as polar because of that shape. The bond dipoles do not cancel each other out. All right, our next molecule to consider is SO3. Sulfur and oxygen are in the same group. They have 6 valence electrons. So if I have 1 sulfur and 3 oxygens, that would be 6 plus 6 plus 6 plus 6. That's 24 valence electrons. There are my connections using 3 single bonds. I'm now going to complete the octet around each oxygen. Now, have I reached 24 valence electrons total yet? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes. So we've already used 24 electrons. I can't add any more. And hopefully you can see that that central sulfur atom does not have access to a complete octet. So like I did earlier with the CO2 molecule, where I didn't have enough electrons to complete the octet for carbon, I had to make a double bond for CO2 and part of that process. Same situation here. For the SO3, I'm going to go ahead and move a pair of electrons from one of the oxygens to create a double bond. Is it going to be trigonal pyramidal like we saw with NH3, or is it going to be trigonal planar? Well, there's no lone pair of electrons on that central atom. The sulfur atom has a double bond, 2 single bonds, and that's it. So because there is no lone pair of electrons on that central atom, this is classified as trigonal planar. So NH3 was trigonopyramidal and it was a polar molecule, SO3 is trigonoplanar. I'm going to go ahead and draw it like that so you can see the trigonoplanar geometry. And so is it classified as polar or nonpolar? Do all of these bond dipoles cancel each other out or not? It looks pretty symmetrical. Those bond dipoles are all arranged in a very symmetrical fashion. So the answer is that these three sulfur-oxygen polar bonds, the dipoles, are oriented in a very symmetrical way, such that they are all balanced. Therefore, these dipoles do cancel each other out. So SO3 is classified as a non-polar molecule. So you can see in my classification slide, I've got NH3 classified as polar, but here is SO3, which is classified as nonpolar. It's very symmetrical. All of the bond dipoles cancel each other out. Now, what you might be thinking is that SO3 is a trigonoplanar molecule. Are all trigonoplanar molecules classified as nonpolar? And the answer is, it depends. It depends on the symmetry of the molecule. Could I have a trigonoplanar molecule in which I don't have that perfect symmetry like I have with the SO3? So here's an example. I've got a carbon in the middle. I've got two hydrogens, one on either side, and I've got an oxygen. I do not have the same perfect symmetry all the way around that central carbon atom. So this molecule, CH2O, because it doesn't have that perfect symmetry, there's asymmetry, the bond dipoles do not cancel each other out. So there's an example of a trigonoplanar molecule that, because of its asymmetry, would be considered polar. So kind of like linear, it could be either nonpolar or polar depending on the symmetry. With trigonoplanar, it could either be nonpolar or polar depending on the symmetry. All right, so now that we know that NH3 is trigonopyramidal and polar, and that SO3 is a trigonoplanar molecule that is nonpolar, I think we are ready to move on to part C of this question. So the instructions in part C say, based on your answers to parts A and B, circle all of the intermolecular attractive forces that each substance can experience. Remember, all molecules can experience London dispersion forces, whether they are polar or nonpolar. Only polar molecules can experience dipole-dipole forces. And then for hydrogen bonding attractive forces, the molecule must contain a hydrogen directly bonded to either nitrogen, oxygen, or fluorine. So with respect to the polarity, it doesn't matter if you're polar or nonpolar. So both of these molecules can experience London dispersion forces. But since SO3 is classified as nonpolar, that's it. It cannot experience the other two. NH3 is classified as polar, so it can experience dipole-dipole attractive forces, and there is a hydrogen directly bonded to a nitrogen, so NH3 can also experience hydrogen bonding attractive forces. All right, in our next question, we're going to complete two more Lewis electron dot diagrams and do that same thing, classifying the polarity based on the shape. So we have completing the Lewis electron dot diagrams for SiH4. We'll start with that one, and then we'll do CH3F. So hydrogen has one valence electron. Silicon has 4 valence electrons. So for the SiH4 molecule, that will be 1 plus 1 plus 1 plus 1 plus 4. That's a total of 8 valence electrons. Once I make my connections from the central atom to those 4 hydrogens, I have used up all of my electrons. So that is a complete molecule, SiH4. It's not linear, it's not bent, it's not trigonoplanar, it's not trigonopyramidal. SiH4 is classified as a tetrahedral molecule. Now we have to decide, is it polar or nonpolar? Let's take a look at the symmetry of the SiH4 tetrahedral molecule. So the SiH4 molecule is tetrahedral. But look at that lovely symmetry. these four bonds, these four polar bonds, the four dipoles, are oriented in a symmetrical way, such that they are all balanced and they cancel each other out. So the SiH4 molecule, because of that symmetry, is classified as a nonpolar molecule. So far we have CO2 is nonpolar, lovely symmetry there. We have SO3, trigonal planar, symmetry, all the bond dipoles cancel out, and now we have SiH4. So the three molecules that we've seen so far on the left are nonpolar, all of the bond dipoles cancel each other out, and then we have one example which I had mentioned earlier, the HCN, which is linear but doesn't have that same symmetry, so that was polar. H2S is bent. All bent molecules are polar. NH3 is trigonal pyramidal. All trigonal pyramidal molecules are polar. And then the CH2O was an example of a trigonal planar molecule that did not have the same symmetry that SO3 had, so that was polar. So you might be thinking, SiH4 is a tetrahedral molecule. Are all tetrahedral molecules going to be classified as nonpolar? And the answer is, it depends. It depends on the symmetry of the molecule, like we saw with linear, like we saw with trigonal planar. With tetrahedral, it does depend on the symmetry. So could you have a tetrahedral molecule that is classified as polar? Well, I'm kind of giving you a spoiler for the one that we're about to do in this practice quiz. You can see it is a tetrahedral molecule that has a carbon in the center, but instead of four identical atoms at the four corners of this molecule, it's 3 hydrogens and 1 fluorine. So if you have 3 atoms of one element and then 1 atom of a different element, that messes up the symmetry and the bond dipoles do not cancel each other out. Even if you had 2 hydrogens and 2 fluorines, so 2 atoms of one type and 2 atoms of another, that would still not be a symmetrically arranged molecule. For that tetrahedral molecule to be classified as nonpolar, all 4 of the atoms at the corner of that molecule would have to be the exact same. So I'm, again, giving away the answer to this next part of the question. So a tetrahedral molecule could be nonpolar if you have that perfect symmetry, or a tetrahedral molecule could be polar if you have 3 atoms of one type and 1 of another, or 2 and 2. That messes up the symmetry. So SiH4, tetrahedral, nonpolar. Here comes CH3F. Hydrogen would be 1 valence electron, and we have 3 of them. Carbon has 4 valence electrons. We have 1 carbon. Fluorine has 7 valence electrons, and we have 1 fluorine. So it's going to be 1 plus 1 plus 1 plus 4 plus 7. So that's 14 valence electrons for the CH3F molecule. I've just used up 8 electrons in drawing those 4 dashes. The only atom that still needs an octet is the fluorine. So that would be 10, 12, 14, and now that molecule is complete. There's all 14 valence electrons. Every atom has an octet except for hydrogen, which only needs 2 electrons. So yes, each hydrogen atom only needs that 1 dash and no dots around the hydrogen. So is the CH3F molecule classified as nonpolar or polar? Well, you already know the answer to that question. So look at the arrangement of those bond dipoles. We have 3 hydrogens and 1 fluorine. These 4 polar bonds, again, 3 hydrogens, 1 fluorine, are not oriented in a symmetrical way like they were for SiH4. And the 4 atoms bonded to the central atom are not the same element. So these dipoles do not cancel each other out. This is a polar molecule. All right, let's move on to part C of this question. So based on your answers to parts A and B, circle all of the intermolecular attractive forces that each substance can experience. London dispersion forces, all molecules can experience those. Dipole-dipole forces, only polar molecules can experience those. And then hydrogen bonding, you have to have a hydrogen in the molecule that is directly bonded to either nitrogen, oxygen, or fluorine. So SiH4 is nonpolar, CH3F is polar, They can both experience London dispersion forces. Only CH3F can experience dipole-dipole forces. And there is a hydrogen, but it's bonded to carbon. It's not bonded to fluorine. So CH3F cannot experience hydrogen bonding attractive forces between its molecules. All right, well, that is the answer to that part of that question. And now we are ready to take a look at question 6. In question 6, it says, the boiling point of a pure substance is a physical property that can be used to compare the relative strength of the intermolecular attractive forces, or IMFs for short, the intermolecular attractive forces between the molecules of that substance. Answer the following questions related to polarity, intermolecular attractive forces, and boiling point. Now let's start with the polarity. Each of these molecules looks fairly symmetrical and balanced, and so if you're thinking, are they polar or nonpolar, I'm hoping that that symmetry would suggest that they are nonpolar. So the bonds or the dipoles in each of these molecules, CH4, C4H10, are oriented in a very symmetrical way, such that they are all balanced. Therefore, the dipoles cancel each other out. Each of these molecules is classified as a nonpolar molecule. Now, can they experience hydrogen bonding? No, there's not a hydrogen directly bonded to either nitrogen, oxygen, or fluorine. Can they experience dipole-dipole forces? No, because they are nonpolar. So they can only experience London dispersion forces. But now you're wondering, how do I decide which substance should have the higher boiling point? Well, in my packet for polarity and intermolecular forces, I had presented some questions related to the relative strength of London dispersion forces. So on this slide, you can see that the boiling points of neon, argon, krypton, and xenon are increasing as you go from top to bottom in this table. And the number of electrons are also increasing from 10 to 18 to 36 to 54. We also see fluorine, chlorine, bromine, and iodine. These are all diatomic molecules. And as their number of electrons increases, the boiling points are also increasing from top to bottom in that table. So the question I had asked that was related to London dispersion forces is the following. What does the data in the table above suggest about the relative strength of London dispersion forces for the members of group 17, such as the fluorine, chlorine, bromine, iodine family, halogens, or group 18, the noble gases, including neon, argon, krypton, and xenon? And so here is the answer to that question. The higher the boiling point, the stronger the attractive forces between the particles. And the strength of the London dispersion forces, or the LDFs, for the elements in group 17 and 18 tends to increase as the number of electrons increases. So iodine has stronger London dispersion forces than bromine, which has stronger London dispersion forces than chlorine, etc. Also, xenon has stronger London dispersion forces than krypton, which has stronger London dispersion forces than argon. So a larger electron cloud is going to have stronger London dispersion forces. So and here's another question from that same packet. The ease with which the electron cloud can be distorted is called polarizability. The greater the polarizability, the greater the dispersion forces will be, and it's going to be a function of the size of the electron cloud. So here we have 4 substances from left to right: CH4, which has 10 electrons total, C2H6, 18 total electrons, C3H8, 26 total electrons, and C4H10, 34 total electrons. So the butane, C4H10, which has the most electrons, and then methane, CH4, has the fewest electrons. The smallest electron cloud had the weakest London dispersion forces and the lowest boiling point, and the largest electron cloud had the strongest London dispersion forces and the highest boiling point. Now let's go back to this particular question. So there's CH4, and there's C4H10. C4H10 has a larger number of electrons and a larger electron cloud, which results in stronger London dispersion forces for C4H10. So the answer to that last part of this table on this slide is that C4H10 should have the higher boiling point. All right, now we've finished with question 6. Let's go ahead and move on to question 7, which is a similar pattern of questions. We're going to take a look at the structural formula, decide if they're polar or nonpolar, and then talk about the intermolecular forces, and then choose which substance should have the higher boiling point. So here are the two structural formulas. The one on the left does not have that lovely perfect symmetry, but the one on the right does. So the polar bonds in C2H5F are not oriented in a symmetrical way. So these dipoles do not cancel each other out. C2H5F is classified as polar. But C2H6, very good symmetry. The bonds are oriented in a very symmetrical way such that they are all balanced. These dipoles cancel each other out, so C2H6 is classified as a nonpolar molecule. Now, can they both experience London dispersion forces? Yes. Doesn't matter if you're polar or nonpolar. Can either of them experience dipole-dipole forces? Well, only C2H5F, because it is polar. And in terms of hydrogen bonding, all of these hydrogen atoms are directly bonded to carbon, not nitrogen, not oxygen, and not fluorine, so neither of them can experience hydrogen bonding attractive forces. How do we decide which substance is more likely to have the higher boiling point? The answer is C2H5F, because it experiences a combination of London dispersion forces and dipole-dipole forces. That combination would be stronger than just the London dispersion forces for C2H6. So stronger intermolecular attractive forces for C2H5F. C2H5F should have the higher boiling point. All right, well, that was question 7. Now let's move on to question 8. Again, a similar pattern here. We have two structural formulas. Neither of them appear to have that perfect symmetry. It looks like both of these are going to be classified as polar. So the bonds or the dipoles in each of these molecules are not oriented in that perfect symmetrical way. So in each of these molecules, the bond dipoles do not cancel each other out. Each molecule is classified as a polar molecule. Can they experience London dispersion forces? Yes, all molecules can experience London dispersion forces. Can they experience dipole-dipole forces? Well, they are both polar, so yes, they can experience dipole-dipole forces. Well, what about hydrogen bonding? Do we see in either of these molecules a hydrogen directly bonded to either a nitrogen or a fluorine or an oxygen? Yes. The molecule on the left, which is C3H7OH, does contain a hydrogen directly bonded to oxygen, so it can experience hydrogen bonding, whereas the C3H7F, all of those hydrogens are bonded directly to carbon, so it cannot experience hydrogen bonding attractive forces. Now, how do we decide which substance should have the higher boiling point? Well, since C3H7OH can experience all three, that combination of London dispersion forces, dipole-dipole forces, and hydrogen bonding attractive forces, we would predict that there should be stronger attractive forces between the molecules for C3H7OH. So that should have the higher boiling point. All right, well, that is the answer to question 8. Now, as we move on to question 9, it's going to involve calculations with heat. So let's go ahead and take a look at question 9. Now, question 9, as you can see, has 3 different parts, A, B, and C. It says, information about salicylic acid, which has the chemical formula C7H6O3, and it's a solid. Information about salicylic acid is listed in the table above. In addition to the chemical formula, we have something called the specific heat capacity. it says it's 1.17 joules per gram degree Celsius. So that means that it takes 1.17 joules of thermal energy or heat to raise the temperature of 1 gram of this salicylic acid by 1 degree Celsius. We also are given the melting point, which is 159 degrees Celsius of this substance. And then finally, we're given something called the molar heat of fusion. And the number is 27.1 kilojoules per mole. That is the amount of heat or the amount of thermal energy to melt 1 mole of that substance. So again, let's just focus on part A, and then we can proceed with the rest of question 9. So in part A, it says, in a certain experiment, a pure sample of 82.9 grams of salicylic acid is heated from a temperature of 25 degrees Celsius to the melting point of 159 degrees Celsius, and the sample of solid is melted completely. So in part A, it says, use the setup below to calculate the amount of heat in joules that is required to heat 82.9 grams of salicylic acid from 25 degrees Celsius to 159 degrees Celsius. Now, we did do a problem like this in my packet for properties of liquids and solids. So here on this slide is an example of a similar type of problem. And I'll just call your attention to the fact that when we're doing these types of problems involving a change in temperature, the heat required to raise the temperature would be mass, so mass in grams, times the specific heat capacity, which has units of joules per gram degree Celsius, and then times the change in temperature. So mass times specific heat capacity times the change in temperature. That's how we're going to solve part A of this question. So the mass has already been filled in for us. That's 82.9 grams. The specific heat capacity is listed in the table. That's 1.17 joules per gram degree Celsius. Now we need the change in temperature. The change in temperature would be a difference of 159 minus 25. So we're heating this sample from a temperature of 25 degrees Celsius to 159 degrees Celsius. That's a difference of 159 minus 25. That's 134. So 134 degrees Celsius is our change in temperature. When we multiply these three numbers together, the grams will cancel out, the degrees Celsius will cancel out, and we'll have our answer in units of joules. So when I pick up my calculator, it's going to be 82.9 times 1.17 times 134. And I get 12,997 joules. I'm not really ready to round off that answer to the proper number of significant figures, so I'm going to go ahead and just leave it like that for now. But I'll tell you that coming up in part C of this question, we're going to need to get to kilojoules. Right now, this is a fine answer. This is in joules, but how do we go from joules to kilojoules? Well, the answer is that we divide by 1,000. So if I take this number, 12,997 joules, if I divide by 1,000, then I can convert from units of joules to kilojoules. And so the reason why that works is because there are 1,000 joules for every 1 kilojoule. So 12,997 joules divided by 1,000, that would give me, when I'm ready to convert from joules to kilojoules, that would give me 12.997 with units of kilojoules. Well, that is the answer to part A. I'm going to move on now to part B of this question. So we've already heated the sample, but now we are going to melt the sample. So part B says use the setup below to calculate the amount of heat in kilojoules that is required to completely melt 82.9 grams of salicylic acid at its melting point. So in the table, the molar heat of fusion is 27.1 kilojoules per mole. It takes 27.1 kilojoules of thermal energy or heat to melt 1 mole of salicylic acid. Now, that is going to be located at the end in terms of the conversion factor. So what's missing? How do I get from grams to moles? And that would be the periodic table. So we need the molar mass of C7H6O3 to go from grams to moles. Because then if I can go from grams to moles, I can go from moles to kilojoules using the molar heat of fusion. I look on the periodic table and I can see that carbon has a mass of 12.01 and I have 7 carbons. Hydrogen has a mass of 1.008 and I have 6 hydrogens. And then oxygen has a mass of 16 and I have 3 oxygens in this formula. So the total of 7 carbons, 6 hydrogens, and 3 oxygens, that would be the molar mass of C7H6O3. And that works out to be 138.118 grams per mole. I'm going to create my conversion factor with grams on the bottom and moles on top. So for every 1 mole of salicylic acid, that would be 138.118 grams. Now I'm set up to go from grams to moles, and then I can go from moles to kilojoules. I'm going to pick up my calculator and do 82.9 divided by 138.118 and then times 27.1, and my answer will have units of kilojoules. So when I do that math, I get 16.266. I'm not rounding off this number just yet because I'm not done. 16.266 kilojoules. Well, if the answer to part A is complete, and now the answer to part B is complete, what are they asking us to do in part C of this question? It says, add your answers to parts A and B together to determine the total amount of heat in kilojoules that is required to heat a pure sample of 82.9 grams of salicylic acid from 25 degrees Celsius to its melting point of 159 degrees Celsius and melt the solid completely. So our answer to part A in kilojoules would be 12.997. Our answer to part B in kilojoules would be 16.266. And when we add these numbers together, on my calculator, I get 29.263 kilojoules. Now I think I'm going to round this off. So based on the fact that 82.9 grams has 3 significant figures, I'm going to round off my answer to 29.3, which would have 3 significant figures. All right, well, that is the answer to this question, but now let's go ahead and move on to a very similar style. This is question 10. So question 10 is similar to question 9, but there's a few differences here. We are still going to be heating a substance, but unlike question 9, where a solid was melted, here in question 10, we're going to be boiling a liquid. So we have a substance, this is ethanol. Information about ethanol, C2H6O, which is a liquid, is listed in the table above. We have a specific heat capacity. We have a boiling point, and then we have the molar heat of vaporization. That would be the energy required to completely boil a liquid. Let's go ahead and just focus on part A, and then we can move on to the other parts of question 10. So here is part A. It says, in a certain experiment, a pure sample of 82.9 grams of liquid ethanol, which is C2H6O, it's heated from a temperature of 25 degrees Celsius to the boiling point of 78 degrees Celsius. And then eventually the sample of liquid is boiled completely. But in part A, use the setup below to calculate the amount of heat in joules that is required to heat 82.9 grams of liquid ethanol. So we're not ready for that molar heat of vaporization. That will be used in part B of this question. So in part A, we're just doing mass times the specific heat capacity and then times the change in temperature. So the specific heat capacity of liquid ethanol is 2.46 joules per gram degree Celsius. So that is the amount of thermal energy or heat that is required to raise 1 gram of this substance by 1 degree Celsius. Now, what's our change in temperature? We're going from 25 degrees Celsius to 78 degrees Celsius. That's a difference of, so 78 minus 25, that's 53 degrees Celsius. Now all we have to do is multiply these three numbers together, because the grams will cancel out, the degrees Celsius will cancel out, and we'll get our answer in units of joules. So 82.9 times 2.46 times 53. When I do that math on my calculator, I get 10,809, and that would be joules. Now, if I need to convert this into kilojoules, I will divide by 1,000. So 10,809 joules. There's 1,000 joules for every 1 kilojoule. So when I divide by 1,000, that would be 10.809. I will need that number later on in part C of this question, but my answer to part A in joules would be 10,809. Or, if I want to go to kilojoules, 10.809 kilojoules. Now, if that's the answer to part A and we're done with that, let's move on to part B, where we're going to be boiling this liquid. So use the setup below to calculate the amount of heat in kilojoules that is required to completely boil 82.9 grams of liquid ethanol at its boiling point. So there's that molar heat of vaporization. It takes 42.3 kilojoules to completely boil or evaporate 1 mole of ethanol at its boiling point. But if I want to go from grams all the way to kilojoules, then the missing conversion factor would be, I've got to go from grams to moles. So first, I'm going to have to calculate the molar mass so I can go from grams to moles. Then I can use the molar heat of vaporization to go from moles to kilojoules. So I've got carbon, hydrogen, and oxygen. 12.01 for carbon times 2. 1.008 for hydrogen times 6. And then I have only 1 oxygen, which has a mass of 16. So when I add up all of the masses of the elements together, my molar mass is 46.068 grams per mole. I'm going to set that conversion factor up with grams on the bottom and then 1 mole on top. So 1 mole of liquid ethanol has a mass of 46.068 grams. Now I am set up to go from grams to moles and then moles to kilojoules. So when I pick up my calculator, it's going to be 82.9 divided by 46.068 times 42.3. And then my answer will be in units of kilojoules. So when I do that math, I get 76.119 kilojoules. I'm not quite ready to round off my answer yet, so let's go ahead and take a look at parts A and B. So there's my answer to part A, 10,809 joules, or 10.809 kilojoules. Here's my answer to part B, 76.119 kilojoules. Part C, add your answers to parts A and B together to determine the total amount of heat in kilojoules that is required to heat a pure sample of 82.9 grams of liquid ethanol from a temperature of 25 degrees Celsius to its boiling point of 78 degrees Celsius and boil the liquid completely. So the sum of 10.809 and 76.119 is 86.928 kilojoules. Now I'm going to go ahead and round off my answer to 3 significant figures, since the mass of the sample has 3 significant figures. So I'm going to call this 86.9 kilojoules as my final answer. All right, well, that is the answer to this particular question. Now, as we move on to our next question in the practice quiz, this is question 11. We are given a vapor pressure and temperature diagram. Let's go ahead and take a look at the details of question 11. So in question 11, it says, the diagram above represents the relationship between vapor pressure. We can see vapor pressure is on the y-axis, and temperature. We can see temperature on the x-axis for two different liquids, X and Y. Answer the following questions related to the information in the diagram. So in part A, it says the normal boiling point of a liquid is defined at a pressure of 1 atmosphere or 760 torr. Use the diagram to estimate the normal boiling point of each liquid. Now, there is a slight dotted line you can make out on this diagram just above 750. So that is intended to be the pressure of 760 torr. I'm going to go ahead and just highlight that with a red line across that diagram. Now I'm looking for where that curve for liquid X intersects that line. So that would be the temperature at which the normal boiling point of the liquid would occur. So I'm going to go ahead and just drop a vertical line where that curve for liquid X intersects 760 torr. And you can see on the x-axis looks like it's somewhere between 40 and 45 degrees Celsius. I'm going to make an estimate that looks like it's approximately 43 degrees Celsius. So that would be the normal boiling point of liquid X. Now, moving on to the curve for liquid Y, when I see where that curve intersects 760 torr, looks like it's around 70 degrees Celsius. So liquid Y has a higher normal boiling point than liquid X, which gets us the answer to part B. Which liquid, X or Y, experiences stronger intermolecular attractive forces? The higher the boiling point, the stronger the attractive forces between the particles. So because liquid Y has a higher boiling point than liquid X, we can say that liquid Y would experience stronger intermolecular attractive forces. Now we're going to change the pressure. So no longer 760 torr, which is the normal boiling point. We're going to take a vacuum pump. And if we use a vacuum pump to reduce the external pressure above a sample of liquid Y, we're going to reduce it down to 450 torr. So I draw a line at 450 torr. Let's see where that intersects the curve for liquid Y. A sample of liquid Y would boil, looks like it's just slightly above 50 degrees Celsius. I'm going to estimate that's 51. So liquid Y, if the vacuum pump reduces the external pressure to 450 torr, liquid Y would boil at a temperature of 51 degrees Celsius. All right, well, that is the answer to question 11. So now let's take a look at question 12, which is the last question in this practice quiz. So in question 12, it says, a phase diagram for a pure substance is shown at right. And in part A, it says to use the information in the diagram to estimate the normal melting point and the normal boiling point. The first thing we're going to do is label the different regions of this phase diagram as solid, liquid, and gas. So the colder temperatures would be on the left. That would correspond to the solid region of this diagram. The hotter temperatures are on the right. That would correspond to the gas region in this diagram. And then in between those two lines, that would be the liquid. So when you're labeling a phase diagram, solid on the left, gas on the right, and then liquid in the middle between those lines. Now, on to part A. Use the information in the diagram to estimate the normal melting point and the normal boiling point. Now, in the previous question, that was 760 torr, but of course, that's also 1 atmosphere. Since this y-axis is labeled in units of atmospheres, I'm going to draw a line at 1 atmosphere. And when it crosses over from a solid to a liquid at that line, I'm going to go find the temperature by drawing a vertical line. So where it goes from a solid to a liquid at 1 atmosphere, that appears to be somewhere between 30 and 40, but it looks like it's approximately 33 degrees Celsius. Now you might say 32 or 34, but that's approximate. I'm just estimating on the x-axis. Now the next transition would be from a liquid to a gas, and that would be at a pressure of 1 atmosphere, the normal boiling point. So I'm going to drop another line where it looks like it intersects that curve. So from a liquid to a gas, somewhere between 60 and 70. Again, I'm going to estimate approximately 63 degrees Celsius. You might say 62 or 64. All right, well, that is the answer to part A. Normal melting point, 33 degrees Celsius. Normal boiling point, 63 degrees Celsius. So on to part B of this question. What phase would exist for this substance if a sample is at a temperature of 50 degrees Celsius? That would be either a gas or a liquid, just based on 50 degrees Celsius, but it says a pressure of 0.50 atmospheres. I'm going to make a little dot on the curve at a temperature of 50 degrees Celsius and a pressure of 0.50 atmospheres. So it's going to be right there on the diagram, would be in the region labeled as gas. So my answer to part B would be a gas. Here comes some phase changes in parts C, D, and E of this question. So here is part C. Based on your answer to part B, if the external pressure on the sample is increased from 0.50 atmospheres to 1 atmospheres, and we're not changing the temperature, so we're going to go straight up vertically on this diagram, that is going to increase the pressure from 0.5 to 1 atmosphere. You can see I'm showing that on the diagram. I have crossed over from a gas to a liquid by increasing the pressure without changing the temperature. So crossing over from a gas to a liquid, that is known as condensation. So gas to liquid. Now moving on to part D. Based on your answer to part C, if the temperature of the sample is decreased, so now we're going to move from right to left horizontally. So we're decreasing the temperature from 50 degrees Celsius to 0 degrees Celsius, and we're not changing the pressure. So as I move from 50 over to 0, I've just crossed over from the liquid region to the solid region. So going from a liquid to a solid, that would be freezing. And then one more question to answer. This is the last question in the practice quiz. Now, based on your answer to part D, if the external pressure is decreased from 1 atmosphere to 0.25 atmospheres, we're not changing the temperature, so we're going to go straight down from 1 atmosphere to 0.25 atmospheres. I've just crossed over from the solid region to the gas region. This would be solid to gas, and that phase change is known as sublimation. So part B, we had a gas. Part C, we increased the pressure and it was condensing from a gas to a liquid. Part D, we decreased the temperature from a liquid to a solid, that was freezing. And then finally in part E, we decreased the pressure and it went from a solid to a gas, that's sublimation. All right, well, that is the last question in the packet. So this is the end of the video. I hope that you found all of the answers and explanations helpful. Thanks for watching and good luck studying for your quiz on polarity, intermolecular forces, and properties of liquids and solids.